Howdy folks, the topic of discussion today is the Shannon-Nyquist Sampling Theorem. I don't just want to talk about what it is, but I want to share a bunch of real-world examples of where it comes up, as personally in my own life I've found the most difficulty with the Shannon-Nyquist Sampling Theorem when actually applying it in the real world. It's quite a simple and straightforward theorem that many associate with signal processing, and then of course it's applicable there, but really it comes out of information theory, and so it affects most of all of STEM, whichever field you happen to come from. It was created by Claude Shannon and Harry Nyquist, kind of independently of one another. They talked about it, of course, between one another at different points, but it's widely thought that it was independently developed between these two pioneers of the information theory space. And so, without further ado, let's dive right in. And I'd first like to discuss sampling, because sampling seems pretty straightforward, right? If we consider something like the stock market data, this is a really good example of sampling. You're going to have a timestamp, you're going to have some price, and as you change the interval that you're kind of looking at it, or the interval that you're sampling it at, it's going to change the way that you kind of perceive what's going on in the data. You could gather it every minute, 5 minutes, 15, 30, you name it. But let's say that you are gathering this data every hour, and then all of a sudden you decide that you want to gather that data or get a look at that data every single minute. That's not going to work out so well for you if you aren't prepared and sampling it. And so each sample would be a timestamp or a date and timestamp and the price. And your sampling rate would be how often are you gathering this data or gathering these samples. Another real-world example that would not necessarily be a time series example would be something like the very popular machine learning iris dataset. It's very widely considered a toy dataset. These are some iris flowers that I took a video of earlier this year from my mom's garden, just to get a view of what it is. But this data set looks a little bit just like this. Here's some of the first few columns. It's a petal length and width and a sepal length and width for different iris flowers. And then there's one other column, which is either setosa, versicolor, or virginica, based on the type of iris flower. And based on the measurements of these flowers, it's widely used again in machine learning for this type of classification. And I believe this data set is about 150 samples, so each one of these flowers itself and its measurements will be a single sample. But if we look really closely at this, you can see that there's a little bit of overlap here between the virginica and versicolor samples of these different iris flowers. And this data set, I think, is 150 samples, if I'm correct. But the question is, how many samples would be enough to pick up on these outliers? If, let's say, 1 in 100 was an outlier here, and you were using this to train machine learning models to be able to differentiate these different types of flowers, and let's say you only gathered 100 samples, is that good enough to pick up on that rate? And then here is a particle I trapped while I was a student. I was taking a particle trapping course. We'll talk about this in more detail later for another real-world example. But when I trapped this particle, the frames that our camera was capturing were each individual sample. And depending on how many samples we were gathering and the rate at which we were gathering those samples affected whether or not we could study the nature of this particle. And so that's where the Shannon-Nyquist Sampling Theorem comes into play. The Shannon-Nyquist Sampling Theorem is really simple and straightforward. It simply just states something along the lines of, to be able to measure the maximum frequency in a signal or in a data set, the sampling frequency of the signal must be 2 times or more than 2 times that maximum frequency. So in other words, if your maximum frequency you expect is 10 hertz, or you expect something to happen 10 times per second, you need to sample at more than 20 times per second. And so this is the simplicity of the Shannon-Nyquist Sampling Theorem. But putting it into practice is not always the most straightforward. Okay, So we're going to consider the simplest theoretical case right here, and to do this, I've generated a 100 hertz perfect sine wave, or at least a simulation of a 100 hertz perfect sine wave that you can see on the chart on the left here in blue or aqua or whatever kind of color you want to call it. But then we are sampling that 1 second 100 hertz sine wave in red here. And you can see initially we are sampling it at 50 hertz, but we know from this generated signal that the only thing in it, since it's a perfect sine wave, is a 100 hertz frequency, okay? And so let me ask you a question. If you expected to measure something happening 100 times per second, but you only took 50 samples across that second, do you think that it would be appropriate to measure that thing happening 100 times per second? I hope that the answer, of course, would be no, because you can see here on the right, we have a frequency spectrum or a power spectrum density. We're putting our sampling of our signal through a Fourier transform, and we're trying to measure the frequencies that are in our signal. And you can see that we have this spike here. This spike is the measurement, for those unfamiliar with Fourier transforms or frequency spectrum, power spectrum density type stuff. And you can see that we have a nice big spike here, damn near at 0 hertz. And that's problematic, because this is a perfect simulated 1 second long 100 hertz sine wave. And so what is this that we're measuring here? What is this that's here in our measurement? Well, it's fictitious noise. It is noise called aliasing. And it's called aliasing because it is an alias of our actual 100 hertz frequency, but it's not at 100 hertz. It's not measuring 100 hertz because our sampling is inappropriate for being able to actually measure 100 hertz. And so with this, in a moment, when I kick off this animation, you'll see that we're going to increase our sampling. And just watch what happens to our measurement on the right as we start to increase our sampling. So here you can see our sampling is beginning to change. We're taking more and more samples across this 1 second of data, and you can see that our spike, or our measurement for the frequency, is starting to shift and bounce around and move around. The magnitude is also starting to grow as well. Now we're over 100 hertz, and you can see it's still starting to bounce around, but we're measuring less than 50 hertz, and which is problematic, but now it's pushing up, and it's moving closer and closer towards the expected 100 hertz frequency we expect to measure. And as it continues, you can see it's getting much closer and much closer. And now that we're above 200 hertz, you can see we are measuring that 100 hertz frequency, and it's actually completely stopped dead in its track. Our spike is no longer moving. As a matter of fact, the only thing that's happening to it is its amplitude is growing, and that's because now we are appropriately sampling our signal to be able to measure this 100 hertz frequency. And we're going to stop here at 300 hertz. But you could see that we could just keep going, and the magnitude would just keep getting better. We would be at a much greater resolution here. But there's no need for us to really go above, let's say, like 201 hertz based off of the theorem. And so how does this translate to our data? Well, these frequencies in data would represent some type of feature that you might be trying to measure. If you don't sample things appropriately, you're not going to be able to measure that feature. And so in order for you to retain all the information that you care about in a data set or in a signal, you need to sample whatever it is that you're trying to measure or study properly. Whether it is a simulation, an animation, whatever you name it, you're going to have to sample it properly. And so there's really two main use cases for the Shannon-Nyquist sampling theorem in the real world, at least. Like I said, the first is that it's going to be used to ensure that you are retaining or capturing all the necessary information that you want to be able to measure. The second main use case is optimization, and all the engineers should be really excited about this because that's mostly what engineers do, is just optimizing things. Okay? If you're trying to measure that 100 hertz frequency from before, and you know that the maximum frequency that's going to be in your data set or in your signal is 100 hertz, you don't need to sample more than, let's say, I don't know, like 201, 202 hertz, something like that. As a matter of fact, you could probably sample at 200 hertz and be perfectly fine, but there are some weird oddities with that, which is why the theorem states that it should be greater than twice the maximum frequency present in that signal. There's some debate about that, but that's just what I found to be best practice for me, at least anyways. But once you get up to a 300 hertz sampling rate, there's really no reason to keep sampling anymore. You're just working with more data. You're making your computer do more work, crunch more numbers. It just doesn't really make sense to sample more than is necessary unless you really need that better resolution. And so with that said, let's get into some real-world examples for these two use cases. The first is pretty simple and straightforward. It's just audio. These are the audio settings in my preferences of Audacity. Audacity is what I use to edit audio from time to time. And you can see here we have a project sample rate and a default sample rate. Both of them are set to just over 44 kilohertz or 44,000 hertz. And the reason why it's set to that by default, I haven't actually changed any of these settings, but the reason why it's set to that is because by default, human ears are capable of hearing frequencies up to just about half of this frequency, just under half of this frequency actually. And the reason why it's set to what it's set at just above 44 kilohertz, is so that we can retain all of those frequencies and all that information so that you can have a high quality audio experience. I recognize that I might not have the most high quality audio experience, but that's why these settings are the settings by default in most audio recording applications or platforms or whatever it is you might be using to record audio nowadays in 2025. As a matter of fact, the reason why radio and like old-timey stuff sounded as bad as it did is because this is the frequency range that it was working at. You can see that this nice big bump right here, we have just above 60 hertz on the low end, and we have just above, let's say, 4 kilohertz on the high end, and all the low stuff wasn't able to be picked up, all the high stuff wasn't able to be picked up. And if I turn this filter on, there's a reason why it sounds as bad as it does, is because you're not getting all the frequencies that your ears would otherwise normally be hearing. You're just picking up this small band right here in the spectrum. Moving on from audio, we go to video games and video animating, rendering. It's really important in all of that. And this is a clip of Tim Sweeney on the Lex Fridman Podcast earlier this year in 2025. This is the CEO and creator of Epic Games, the company that makes Fortnite. And this is a clip of him talking about him considering and having to think about and use the Shannon-Nyquist Sampling Theorem in creating video games.
And so when an object is up close to you, you want to render it with a lot more polygons than when it's far away. But one of the cool principles of mathematics is the Nyquist Sampling Theorem that says if you're trying to reconstruct a signal, there's a limit to the amount of data you need to bother capturing. If you want to render a texture at a certain resolution, then you never need more than twice the pixels than in the texture that you have on the screen. And that, that's called the Nyquist limit. And so one of the challenges of computer graphics is, given the need to render objects at extreme close-up distances and extreme far-away distances, you always want to be able to generate the right amount of geometry so that you have enough to be indistinguishable from reality, but not any more than necessary.
And the thing is that the Shannon-Nyquist Sampling Theorem is evidently important enough to Tim Sweeney that he had to bring it up twice throughout this podcast. So here's another clip.
Sorry, I'm just loading it in. Just imagining together in one scene graph, 10 million people interacting. What a cool world that is.
Sure. Well, 10 million people, you have less than 10 million pixels on your screen. So what does the Nyquist sampling theorem say? It says that you don't need full overhead for every player. You need to render the players who are around you and some approximation of everything else.
Yeah, Tim, but there's also a networking component.
Yeah.
You're speaking to the rendering, but oh boy.
Of course, I will leave a link to this podcast in full in the description down below for those of you that are interested. It's a fantastic listen. I strongly recommend that you listen to it if you're interested in any of this type of stuff. But obviously, as you can see, straight from the horse's mouth, if that's what that's how the saying goes. The Shannon-Nyquist Sampling Theorem is incredibly important, not just for a smooth, high-quality video experience, but also an optimization type of situation. Here is the particle, like from before, that I had trapped, and to study the Brownian motion of this particle, that was the whole point of setting up this experiment. This was while I was a student taking a particle trapping course. It was not a particle physics course, it was a particle trapping course. It was mostly about, constructing and setting up the different apparatuses, or not apparatuses, but experiments for trapping particles. And we had to consider both cases of using the Shannon-Nyquist Sampling Theorem in this experiment. The first thing that we had to consider was, what is the maximum frequency that that any trapped particle we trapped could oscillate at? And so we had to construct our experiment in a way such that there was a limit to how fast these particles could oscillate at, or how frequently, I should say, these particles are able to oscillate at. I remember it had something to do with voltage. I don't quite remember. And if I'm being completely honest, this was like more than a 6-hour-long lab in college. It took absolutely forever, just between the setting up, the calibrating, then actually trapping a particle, which took the longest. Don't do particle trapping unless you are extraordinarily patient and tedious. I did not like it very much. I mean, it was cool. That's why I took this video. I'm happy I went through it once, but it was one of those things where it's kind of like, okay, I did it once. I don't need to do it again type of a thing. But then from an optimization perspective, you can look down here at the bottom and you can see that the setting is at 61 frames per second, which is more than enough for us to be able to measure the frequency or the Brownian motion of this particle. But I believe that this camera had numerous settings for the frame rate on it, and we just chose whichever one was the closest to whatever our maximum frequency was based off of how we constructed and set up the experiment. Going from just laboratory physics to astronomy and astrophysics, this is a pulsar. If you've watched videos on my channel before, you probably know that I study pulsars in one way or another. For those unfamiliar, these are stars with beams of light coming roughly from about their poles, and they spin very, very precisely. And one of the things that I do is I try to measure and study the spin and the evolution of the spin of these types of stars, and I do that really with two telescopes. This one is NICER. It's currently in operation. It's been in operation since 2017. And this is RXTE. It ran from 1995 to 2012. And with both of these missions, I should state that I'm not affiliated at all with NASA or these missions. I just use their archival data, which is public and available for people to be able to look at and to get access to try to measure the things that I'm measuring. Now, these pulsars can spin very, very fast. The fastest one that we know of spins 716 times per second. So, obviously, one of the bottlenecks, or the things that I need to think about, is that there's a limitation to what telescopes I can actually use. With NICER, NICER is capable of recording timestamps of 300 nanoseconds resolution. And RXTE, with its PCA module, because there's multiple modules aboard it, it was capable of recording timestamps of 1 microsecond. So that's 1 million samples per second, at least in theory. So both of these two missions, NICER and RXTE, were more than capable of gathering really high-quality data so that I could measure the spin of really any of these pulsars I decided to look at. And here is the last example that I want to give, because actually as like a day job, what I do is I do like data engineering, kind of software engineering, a kind of hodgepodge of a lot of that stuff. And this is pricing data for different gasoline or fuel types for an individual gas station. Here's another one from another gas station. Here's a third one. There's a whole bunch of these, and I was tasked with, we were doing some feature engineering, trying to figure out the probability that the price of gas would change tomorrow based off of previous behavior, things like that. Again, in a data science, data engineering kind of scope, that would be considered feature engineering. And you could see that, like this gas station in particular, the price of gas is changing all the time, like almost every day. This one is changing, it was changing a lot at the beginning of the year. Now it's not changing all too much. It's gone up in price, but not by too much. And then this one's kind of a little bit all over the place. It has long stretches of not changing, other stretches of changing. But all this data, this pricing data, is gathered every single day. The price of gas at all these gas stations only changes day to day. It doesn't change more than that. But in order for us to do this probability feature engineering type of a thing, where we were creating an index that would be like sort of like a probability measure that the price of gas would change tomorrow, or really it's just a measure of the volatility of each one of these individual gas stations. I don't want to get too deep in the weeds about what it actually was about, but this data, as I said, is gathered every single day. And what was the maximum frequency that it could change at? It could change, well, every single day. And so if we are gathering the data every single day, and it's capable of changing day to day, are we sampling well enough to be able to do anything with regard to the frequency of this? The answer to that is no. We aren't sampling in accordance with the Shannon-Nyquist Sampling Theorem. Except the thing is we can't really do any better than sample once a day. We could sample 3 times a day, but it would be a waste of time, because the price of gas is not changing more than once a day at most. So what you would do in this case is you would just take one of these different gas prices, and you would just duplicate the price 3 times across a single day. So you would take one of these collected data points, and we just took one, and you set the same price at midnight, 8 a.m., and 4 p.m., and then the next day was the next price, and you had 3 data points for every single day to fulfill this requirement that the sampling frequency was greater than twice the maximum frequency expected in the dataset. And that is how we were able to establish sort of like probabilistic, I don't know if you want to call it a machine learning index, but it's how we generated this new feature that would help us make a prediction as to how likely or not the price of gas would change tomorrow given previous behavior, especially for gas stations. I shouldn't say it like this one, but like this one where there are long stretches of the price being pretty consistent over a good period of time. So, folks, that is the Shannon-Nyquist Sampling Theorem. It's incredibly important. It's incredibly simple. It's something that you need to think about when you're doing any of the work that you're really doing. Unless you're doing strictly analytical work that's on a whiteboard or a chalkboard or a blackboard or just on pen and paper, you're not generating any plots, you're not doing anything, then maybe you don't need to think about the Shannon-Nyquist Sampling Theorem. But otherwise, if you're in STEM, you need to consider the Shannon-Nyquist Sampling Theorem, especially to ensure that you are sampling things properly and that you're actually going to be able to measure what it is that you want to measure. And for the engineers in the audience, you need to make sure that this stuff is being measured efficiently. So, folks, that'll do it for this discussion of the Shannon-Nyquist Sampling Theorem. If you've got questions, comments, or concerns, don't hesitate to let me know. Thank you all very much for watching. I hope you found this beneficial in one way or another, either informative, educational, entertaining, whatever you want to call it. Thank you all very much again for watching, and I hope to see you all again next time.